We go on to sampling of continuous functions. We need to realize that the Z transform is only taken on discrete signals. So therefore, if you've been given a continuous signal, say f of t, and that has been sampled at time intervals t, which are separating equally spaced points, then we can be able to get a sampled signal expressed as the sum of fk multiplied by delta of t minus kt from k equal to 0 up to infinity. Note that if it is sampled, it will be signified by f star of t. And note that by sampling a continuous signal at discrete time values, then the continuous signal can be expressed as a discrete signal. So in order for us to be able to take the Z transform of a continuous signal, this statement is very, very important, because we will be able then to do sampling on the continuous signal and then be able to process it and take the Z transform as if it is a discrete signal. Let's do some examples. Given, first of all, f of t is equal to cos 3t, and it has been sampled at the formula t equal to kt for k an element of real numbers. Note that the first thing we need to do is to substitute for the value of t is kt, so that we have cos of 3 kt. Also, when we are going to take the Z transform of cos 3 kt, we need to recognize that we have cos 3t multiplied by k. And then we go to rule 12 of the Z transform tables and be able to get this formula: Z into Z minus cos 3t divided by Z squared minus 2Z cos 3t plus 1. Once again, we have now f of t equal to e to the power negative t. Note now, t has been given in the interval 0, 0.1, 0.2. Note that they are equally spaced, so therefore capital letter T is the difference between the time intervals. Therefore, we say that capital letter T is 0.1. So by substituting in place of T, by substituting KT, we've got the sampled discrete time signal, and therefore we can be able to take its Z transform. And I believe that we used rule 6 to get Z over Z minus e to the power negative 0.1. Then number 3, we have f of t equal to t squared. Again, we use t equal to kt to sample this continuous signal. We get therefore k squared t squared. Note that the Z transform is linear, and t usually is just a number. So we can take out the coefficient t squared and then be able to find the Z transform of k squared using rule 4. As noted before, I used the linearity in order for us to take the Z transform of t squared k squared. So one of its properties of the Z transform is linearity, where you can take the Z transform of the sum of two signals and you separate them, and it's just the same as the Z transform of the individual signals. Also, the Z transform of C multiplied by a signal is C times the Z transform of that particular signal. Note the example that we have here. We have 1 plus 3e to power 2k. So we'll take the Z transform of each term. This will help us also when we are solving the differential equations using the Z transforms, because most of the time it's sum of constant coefficient terms. Therefore, we have to use the linearity of the Z transform in order for us to take the Z transform of each of those terms. Rule 2, I believe, says that the Z transform of 1 is Z over Z minus 1. And then rule 6, the Z transform of e to the power 2k is Z over Z minus e to the power 2. Note we are multiplying that by 3, and therefore we can be able then to add these two quotients. Note that we do the cross multiplication of those terms, and then the denominator, you multiply them out so that we simplify the whole expression. Check out whether the numerator is correct. We go then to the first shift theorem, which is the delay. We've got the discrete signal xk. It has been delayed by k naught. Then it is represented as xk minus k naught. And then it will be given to be 1 over z to the power k naught times x of z. This is the Z transform of the delayed signal by k naught. Note once again, the Z transform of x of k minus k naught is 1 over z to the power k naught multiplied by the Z transform of the original discrete signal xk. Let's take an example here. We have the original signal to be half to the power k, and it's also a causal sequence. And then we have the delay of xk minus 2 given to be yk. So that means y of z is 1 over z squared. Note that the power of z is always k naught, and our k naught in this case is 2. So we have 1 over z squared multiplied by the Z transform of the original signal. So we have 1 over Z squared times Z over Z minus half. This is definitely 2Z over 2Z minus 1. When we simplify it, that's the particular answer that we get. Once again, we will have 1 over Z to the power k naught. So we always need to take note of the delay or the value of k naught. Then we go to the advancing shift, where you have a single step and a two-step advance. The single step is recognized as xk plus 1, and the two-step is xk plus 2. The Z transform of xk plus 1 is zx of z minus zx0. Note that x0 is the initial condition. Also for xk plus 2, we'll have z squared x of z minus z squared x0 minus zx1. x0 and x1 both are initial conditions, which will always be given when we are solving equations using the Z transform. This is the general formula that can be used to get all the formulas that are needed at that particular moment. Let's go to the inverse Z transform, which will be helpful when we solve differential equations using Z transforms. So let's start here. Determine the inverse of the Z transform. We know that when we have the Z transform, we take the inverse Z transform so that we get back the discrete signal. So once again, because of the linearity, we take 4 out and then take the inverse Z transform of Z over Z minus 4. That gives us 4 multiplied by 4 to the power k for k greater than or equal to 0. Please make sure that you have the rules or on the Z transform tables so that you understand. If it was Z over Z minus 3, we would have 3 to the power k. Now, what if we get a complex Z transform? Then we'll have to make use of partial fractions. But before we do that, note that what we do to the numerator, we take out Z so that we get Z plus 2 inside the brackets. And then we transfer Z to the left-hand side. Reason being, once you've taken the partial fractions, A and B will be just constants, and all the Z transforms on that table have Z in the numerator. Once we've got the partial fractions, we multiply Z back up so that we can be able to find the inverse Z transform. I need you to note also that in order for me to be able to get the Z transform of the first term, it was either multiplying this term by 3 over 3 so that I get 3Z in the numerator. But then I chose to take out 3 and then have Z minus Z over 3 in that denominator. And I know that Z over Z minus 7 over 3 gives me Z over 3 to the power k, and 3 times 10 in that denominator will be equal to 30. And then we go to the second term, which was Z plus 1 in the denominator, which is just Z minus negative 1. That is why we have a negative 1 to the power k in the second term. Please check whether the values for A and B are correct. Either using manually algebraically using pen and paper, or may use any software, Mathematica or MATLAB. Once again, we will need to use the partial fractions because on the Z transform tables we don't have a product of 2 terms in the denominator. Once again, first thing first, take Z to the left hand side so that you get f of Z over Z, and then be able to get the partial fractions. And then I got 1 and negative 1, and then multiply with the Z both terms, and that's the final answer that we got. Once again, we have a complex function, but note that we don't have a common term which is Z, or common variable which is Z in that numerator. So this is one option. There's another option that I'm going to show you. This one is just to go straight and find the partial fractions of that expression, which are those. And then we introduce Z over Z in both terms because the numerator needs to have a Z in order for us to find the partial fractions. So now we end up with a 1 over z in both terms, and therefore we have to recognize that we end up with the first shift situation. Therefore, the power of z is being 1 in both terms, because we've got 1 there and we've got 1 there. So that means the value for k naught is 1. So you will have x of k minus 1. Therefore, the z transform of z over z plus 1, which is negative 1 to the power k. But because of that shift with k not equal to 1, that power has to be k minus 1. Once again, for the second part, we were supposed to have 3 to the power k, but because of that term, we end up with 3 to the power k minus 1. I need you also to realize that negative 1 to the power k minus 1 is the same as negative 1 to the power k multiplied by negative 1 to the power negative 1. So that means all in all, we'll end up with negative 1 over 4 minus 1 to the power k if we simplify. Once again here, 3 to the power k times 3 to the power negative 1 will result in 1 over 3 times 3 to the power k, and then you multiply that to 7 over 4, giving us 7 over 12. But then let's go to the next option. What if we decide to take out z in that numerator? Will it then simplify to give us the same answer as this one? Note, if we take z out, we'll have 2 plus 1 over z. So that we'll have f of z over z on the left, and then be able to work out our partial fractions. I can assure you the answer is the same as in the previous slide. We go to number 5. Now we encounter a different situation where the numerator is divided by a single term in the denominator. So what you do is to divide each of those terms by z cubed. Note that what we have, we end up with 1 plus 2 over z plus 1 over z cubed, which is a series, hoping that you realize that 1 is divided by z to the power naught, 2 is divided by z to the power 1, and then between z to the power 1 and z to the power 3, we have 0 over z to the power 2. Therefore, it means that this sequence, which is represented by that z transform from the definition of the z transforms, will be 1, 2, 0, 1, 0, dot, dot, dot. Number 6, note that 1 is divided by z to the power 0. And between z to the power 0 and z to the power 2, there is z to the power 1. So there is one term here in between. That means we have 0 as its numerator. Hence, we have 1, 0, 3. Note now the next term is negative 2 over z to the power 9. So it means there is z to the power 3, to the power 4, to the power 5, to the power 6, to the power 7, to the power 8 that are in between with numerators 0. Hence, we've got zeros there, and then we've got negative 2, and then all the other terms that come after 2 over z power 9 are zeros. Once again, we go to number 7. Now we have a combination of two terms. Recognizing that 1 plus z is being divided by z cubed, which means that what you need to do is to divide each of those two terms by z cubed. So we'll have 1 over z cubed plus z over z cubed. Note then that z over z cubed gives us 1 over z squared. So you end up with 1 over z cubed and 1 over z squared. But it has to be written in an appropriate order. Hence, we start with 1 over z squared, followed with 1 over z cubed, and then 3z over 3z plus 1. These two, remember, our series says when they are causal, they start from z equal to 0. So the power of z power 0 is 0. The power of z to the power 1 is also 0. And then we've got 1 for z squared, and we've got 1 for z cubed, and then 0 for all the other terms, dot, 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 plus the z transform, the inverse z transform of 3z over 3z plus 1, which is negative 1 over 3 to the power k. Number 8, once again, we've got a combination. 2z cubed can be divided by z squared over 2z plus 1. Also, 6z squared can also be divided by z squared plus 2z plus 1. Reason being, z squared will cancel z squared from z cubed, and z squared will cancel. Note, that's exactly what happened here. We ended up with 2z in the numerator divided by 2z plus 1 and 6 over 2z plus 1. Note that we have to divide the first and the second term by the whole denominator, and then we cancel the terms that need to be cancelled, and then we are left with 5z plus 1 divided by z squared into 2z plus 1. This requires partial fractions. Therefore, we need to get those partial fractions. Also remember, when we have z squared, a will be divided by z, b by z squared, and then c by 2z plus 1. We get those partial fractions, and then thereafter, remember, these are the partial fractions that we got: a is 3, b 1, and c negative 6. And then we add them to those two terms that we had there. We add them up, simplify. Note that you've got that term and that term cancelling each other out. So we end up with those three terms. Note we have 2z over 2z plus 1. Its inverse z transform is negative half to the power k, but these ones, they start with 0 for z to the power 0, and 3, and then 1 for z squared, and then 0 for z cubed, and all the other terms. We move on to differential equations, but then we start with how we formulate the differential equations when we've been given a discrete time signal processing system. I need us to note that we have xk as the input signal, rk as the output signal from the summing junction, but an input signal to the delay block. And then the output signal of the whole system is yk. But then we've got a feedback into the summing junction, which is alpha, and in this case it is minus. So I need us to be able to recognize that, and then we'll note that if we start with the summing junction, we need to recognize all the signals that are going into the summing junction. The first signal is xk into the summing junction. The second signal that comes in is alpha multiplied by yk, and you need to subtract it because it has been given that it has to be subtracted. So we have xk minus alpha yk going into the summing junction, producing rk. So that means the summing junction gives us the formula xk minus alpha yk equal to rk. And then we have rk and yk with a delay block in there. Therefore, we have rk equal to yk plus 1. We can therefore be able to formulate an equation with two equations both equal to rk. And we can be able to get a proper differential equation equal to the input signal. Let's take a look. As we said, we have yk plus 1 equal to rk, delay block. We've got rk equal to xk minus alpha yk, summing junction. Then both of them are equal to rk. Then we can equate them. And that's the formula we have. Everything that has got y goes to the left, and the input signal remains on the right hand side. Now here's a more complex one. Let's start with the summing junction. Once again, everything that goes into the summing junction, all the signals, we have xk, that's the first one, and we recognize xk here. And then the next one is minus a vk, that's what we get. And the next one is plus b yk, that has been recognized. Now we go back. Out of the first delay block comes out vk. So rk is equal to vk plus 1. That's what we have. Rk equal to vk plus 1. Out of the second, we have vk equal to yk plus 1. Also, we can be able to say rk and the two delay blocks yields yk plus 2. And remember, we had said vk plus 1 is equal to rk. So that means rk is equal to yk plus 2. Now we combine all of this into that formula for the summing junction. Rk has to be substituted, and our rk is yk plus 2. Vk has to be substituted, it is equal to yk plus 1. And then we sort it out. So in place of rk, we've got yk plus 2. In place of vk, we've got yk plus 1. And then we take all the outputs, which is y's, on the left-hand side, and we're left with the input, which is xk, on the right-hand side. Looking at these exercises, summing junction, first thing that you need to recognize is that the xk goes in, minus half vk goes in. That's your summing junction, producing rk. And then rk is equal to vk plus 1, and vk plus 1, vk is equal to yk plus 1, and rk is equal to yk plus 2. You can be able to formulate a differential equation. Know that you need, every time you get a system of this nature, do the labeling and then work it out. We solve the differential equation. The first thing we do, take Z transforms for each term. Secondly, substitute initial conditions and simplify. Make y of z or x of z, depending on what you have been given, the subject, and then determine the inverse Z transform to solve the equation. Let's do this. Here is our differential equation. First thing, take the Z transform of each term. Xk plus 1 is given by Zx of z minus Zx0. All of this is multiplied by 2 minus the Z transform of xk is always x of z. The Z transform of 2 to the power k is z over z minus 2. Then, next step, substitute the initial condition x naught. Substitute it in, recognizing that there is a 2 there and a 2 there. That gives us a 4. Make x of z the subject. This is what we'll end up with. X of z will be equal to z over z minus 2 plus 4z. I simplified that, and then thereafter took out the common factor in the numerator, which is z, so that we have 4z minus 7 in the numerator. And then denominator, remember there is that 2z minus 1 that has to be transferred. So we have 2z minus 1 into z minus 2. In order for us to take the inverse Z transform, we have to take partial fractions of the right-hand side. The terms that I've got are A 1 over 3 and 10 over 3 for B. And then recognizing that the second term has got 2z minus 1 in the denominator, so it means I have to have a 2z in that numerator. And then I recognize that 10 is 5 times 2. So I split up 10 to 5 times 2 so that I have 2z there. So that the inverse Z transform of that term becomes half to the power k. Hence the formula or the solution is that one. Number 2, we do exactly the same. Z transform of each term using our Z transform tables, recognizing that there is a 3 that multiplies yk plus 1. So we have to put the Z transform of yk plus 1 in brackets so that we multiply by 3. Substitute the initial conditions, y equal to 0 and y1 equal to 1. Factorizing that denominator after making y of z the subject, and then take z from the numerator to the left hand side so that we're left with 1 over z plus 2 into z plus 1, and take partial fractions. That's exactly what we did. And then we got a to be negative 1 and b to be 1, and then multiplied out by the z, and then took the inverse Z transform to yield that solution. Please do the exercises number 3 and number 4, solving the given differential equations. We quickly move on to the transfer functions. I need you to recognize that the transfer function contains all the information about the stability of the system, and how you get the transfer function g of z is equal to y of z divided by u of z, or y of z is always equal to g of z multiplied by u of z. Note that from the transfer function, we need to get the poles. If all the poles are within a unit circle is a circle of radius 1, then we know that the system is stable. But if you discover that there is one or more poles that are outside the unit circle, then the system is stable. Even if all the others are inside, if there is even one that is outside the unit circle, then that means the system is unstable. Then we have a third condition. If one or more poles lie on the unit circle while others are within the unit circle, then the system is marginally stable. Remember, others must be within and one or more could be on the unit circle in order for the system to be marginally stable. Now let's do some examples quickly. Given again differential equations, we know now what to do, and we have been asked to determine the transfer function and comment on the stability of the system. So first things first, we know when we're given a differential equation, we take the z transform of both sides, noting that the z transform of uk is u of z, and then make y of z the subject, and recalling that y of z is always equal to g of z multiplied by u of z. So that means 1 over z squared plus 3z minus 1 is g of z. Okay, so commenting on the stability, we know that from the transfer function, we'll take the denominator, equate it to 0, and factorize. So out of the two factors, we discovered that one lies within the unit circle, but the other lies outside. Therefore, the system is unstable. You can use your calculator and press the key SD on your Casio. If you are using Casio, any of the Casio, or you can even be using a sharp calculator, it will be able to give you the value of those two poles so that you can be able to determine which one is lying within a unit circle and which one lies without. Then we go to number 2. I'm hoping that we notice something here. On the right hand side, we've been given uk plus 1 minus uk. So that means the same rule, rule 16, which applies to yk plus 1, will apply to uk plus 1. So now take the z transform of each term, noting that also we'll have z, u of z minus z, u0 for uk plus 1 minus u of z for uk. And then on the right hand side, make u of z the subject and substituting the initial conditions throughout, and you can see that y of z will be z minus 1 divided by 2z squared minus 2z plus 1. Therefore, that is the transfer function g of z. And therefore, for stability, you take the denominator of the transfer function, equate it to 0, and factorize. And we note that even when you draw these two poles, they both lie within a unit circle. And even when you check their lengths, you'll find them their length is around 0.707, which is square root of 2 over 2 or 1 over square root of 2. So we recognize that they are both poles lie within a unit circle, and therefore the system is stable. Number 3, once again, we're given an equation and we are supposed to find g of z. Please make sure that you give us the formula for g of z when you've done your solution. And then for stability, make sure that the denominator of your transfer function is equated to 0, and you show us the factorization and show us the poles. And then both poles lie outside the unit circle, so the system once again is unstable. We move on to the impulse function. Note that delta k, which is a sequence 1, 0, 0, and 0 everywhere else, is called an impulse sequence, and its z transform is 1. And now we end up with y of z equal to g of z times u of z, which is our transfer function. And if our input is uk and corresponding to the output yk, then that situation holds. But then if yk is the impulse sequence delta k and the system initially quiescent, meaning all initial conditions equal to 0, then the output sequence changes to y delta k, and it is called the impulse response of the system. So if we want the impulse response of the system, we are looking for the sequence y delta k. Note that the z transform of y delta k is capital letter Y delta of z, which is exactly equal to g of z. Hence then, in that formula, y of z equal to g of z, u of z, in place of g of z, we'll have y delta of z. Let's do some examples. You've been asked to find the impulse response of the system. You're given the transfer function. The first thing that you need to recognize that y delta of z is equal to g of z, because we've not been asked to find the inverse of the transfer function. We've been asked to find the impulse response, which is y delta k. So therefore, we need to change the notation from g of z to y delta of z. We use the same format of finding the inverse of a given z transform, partial fractions, multiplied throughout by that z which we had taken to the left, and we end up with y delta of z in that format, and the inverse of y delta of z then is the impulse response. Please note the only difference is the notation. Number 2, we have g of z again is 5z squared minus 12z divided by z squared minus 6z plus 8. First things first, change the notation. Recognize that g of z is equal to y delta of z. Also in that numerator, take out z so that you take it to the left hand side. Note that as you continue, you don't use g of z, we are using y delta of z. And then find the partial fractions and then get the inverse z transform of y delta of z, which will be the impulse response.